Okay. Hello, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my real pleasure to introduce our speaker, Professor Na Li. Professor Li is a Gordon McKay Professor in Electrical Engineering and Applied Mathematics at Harvard University. She has made great contributions to control, optimization, and machine learning. Her research lies in control, learning, and optimization of network systems, including theory development, algorithm design, and applications to real-world cyber-physical societal systems. She has received many prestigious awards, including NSF Career Award, Young Investigator Awards from Air Force Office of Scientific Research and Office of Naval Research, and Donald Ackerman Award and McDonald Mentoring Award. The title of her talk today is Real-Time Distributed Decision-Making in Network Systems. Please join me in welcoming her.
Thank you, Joran, for the introduction, and thank you for the invitation. Also, thank you everyone for listening to my talk. So today I will share of some of our recent work actually in the past 2 or 3 years, what we did for do the real-time decision-making to bridge learning and control for physical systems. And this is a joint work with many collaborators, and here just the main contributors, Guannan, Yinyin, Yujie, Xin, they are either my current student or my former student. So Guannan is on job market right now, and Yinyin, Yujie, and Xin, they will be on job market. So if you have nice position, please let me know. Let's do a very quick start of motivation. So I think in the past decades, we have seen major revolution in the sensing, computation, and the communication, so which has boosted our autonomous decision-making significantly. So when we look around, so we notice that more and more connected smart devices. So they generate a huge amount of data, and the data is communicated either to the cloud or to the edge servers, so which is processed by powerful computers and advanced algorithms. So people have abstract the system to cyber-physical systems. So when people referring as cyber-physical systems, the focus is to integrate the physical layer and decision-making layer by the sensing, communication, computation, and actuating tools. So like when we're looking around, so there's a fundamental difference compared with the decision-making that's in a data center. The reason is the sensor has been spread out at different locations, and we would like the devices to making fast process and making fast decisions that can adapt to the changing environment quickly. So you can imagine this bring a huge fundamental challenges, and like here are just examples. So once we connect all the devices, the system has become larger and larger scale. So it's hard to imagine what kind of algorithm can really handle such a big number of devices. And when we try to coordinate the devices, so we definitely need using communication. But no matter what kind of communication we're going to use, every communication technologies come with their own challenges. We have been seeing the latency in the communication, we have seen the packet drop, and also communication will subject to cyber attack. So besides those challenges, now, because we're trying to integrate the physical system and decision-making, and also the human in the loop. So this growing complexity when we're trying to integrate all the different components together, and nevertheless, all the things also bring additional uncertainties into the decision-making. So what uncertainties we will mean, so that's going to be the focus of this talk. So bottom line is there's a lot of opportunities when we're using all the devices, but there's a lot of challenges. And all the challenges, especially they bring challenges into the decision-making algorithms. So I'm going to focus on uncertainty to illustrate some perspectives. So the first challenge, like for the uncertainty, so every time if we talk about different application people, so people will have different definition for the uncertainties. So here in this talk, I'm going to put them in 2 different categories, but sometimes they are actually unclear which category is really belonging to. So the category I'm going to put into, like first one is internal uncertainty. So what internal uncertainty means, so this lot, like the system getting more and more complex, and it's very hard to understand every parameter of the systems. So like for the system itself, even we put it into the very controlled environment, it's very hard to know exactly how each component is affecting the other. And I'm putting very different examples, like from the robotics to the autonomous manufacturing to the human body, right? We know like we can see the outside, but it's very hard to know inside how exact interaction have been happening. So that's what I'm referring to as internal uncertainty. So the second type of uncertainty I'm going to refer to, I call it as external uncertainty. So what's the internal uncertainties I'm going to mean? Like depending which perspective we're going to really look at the system. So when we think about driving, I think for the control, for the like how really driving the car, how exactly the car is going to move, this is pretty understandable. But in the transportation, if I driving from my office to my home, and when I try to budget, okay, do I have enough time to go to pick up my kid? It's actually becoming harder even I have the current traffic map because the traffic is changing. And this is not just about the human transportation. And when we look at the data center, the robot request is also time varying. And sometimes those patterns is very hard to abstract, right? Do we really have a seasonal pattern, daily pattern, and there's always going to be variations. And speaking of the like additional things, like think about the environment, the nature. So this is the wind generation because I've been working a lot of work on the power management. So when we're doing the power management, the fundamental difficulty is to handle the internal uncertainty. Right? This is the example about how wind generation has been changed within a month. And you can look at for different day, they look very different. So it's posed a lot of challenges, like how can I make my decision if I want to schedule certain kind of demand? And like there's another news, even if we're not really thinking about renewable energy and just using the traditional power generation or other type of demands and traditional generator and traditional supply, but the environment is changing. And this is a very sad news this year, right? How Texas is preparing for the grid for the climate change. So like putting both of them together, what I want to focus on here is this. So when we look at internal uncertainty, so what we can do, because I don't know much about my system, but I have my system. So what I can do is I can do my decision making, I can observe what's coming, and I can, based on my observation, to get better and better understanding of the model. And I think this fits into the reinforcement learning framework very well. So that's kind of the first type of the decision making that we are focusing on. How can we make in the real-time decision making to getting more data, to understand my system, and then making better decisions? And then the other one, I'm going to focus on a different perspective. So as I mentioned, for this perspective, I'm going to focus on the time varying uncertainty that's brought by the external environment. So I'm not going to talk about how I'm going to really predict the environment. So the thing I'm going to talk about the decision making. So I know my external environment is changing. So how can I put in that perspective into my optimization and control? So in that sense, I can either guarantee the worst case guarantee, or if I have some average prediction, I have some statistics about the external environment, can I make a better decision? So like you can imagine, like the system I brought up very beginning, they have both of uncertainties and they have like different sorts of uncertainties. So ideally, we would like to merge them together. But in today's talk, I'm going to focus on them separately. So first, let's just think about very controlled external environment and very stationary environment. Just think about how can I do reinforcement learning to understand my system better. And the other one, I'm going to assume I know everything about myself, my model, and I want to taking care of the decision making, how to hedge the future risk. So like in particular, so I will only focus on like the two parts of the talk. So the first part of the talk, I'm going to talk about the scalable reinforcement learning, because as I mentioned, the system become larger scale. So we need to do some distributed coordination. So how can we really do it? And the second one, I'm going to focus on just about uncertainty, online optimal control, and how I'm going to use in some prediction to making better decision making. So let's dive into the first part, like just about learning the internal uncertainties. So the motivation, like for this group, like I can go very quick. So we have been seeing a lot of exciting news in the reinforcement learning, and this like AlphaGo and the DeepMind going to play the video games. So I would say all the things generating a lot of excitement. So the reason why it's so exciting, because when we look at this one, like when I played all the games, so what's uncertainty? I want to say the system that uncertainty is actually coming from the other person. It's very hard to imagine or to guess what exactly the other person going to work to play. So I would say, and that is really very complex and online unknown model. And for those type of RL, what it's been doing, right? I really don't need to really model the human very well. What I can do is just by playing the game again and again, and observing the state, the reward, and I'm going to take action. And based on those iterative learning, so I can eventually learn a good policy, a good like gameplay policy. But when we look at this like success and thinking about the examples I brought at the very beginning about the societal system, like transportation, manufacturing, and like the power system. So the one fundamental difficulty is like, how can I really scale those algorithms to the societal system? And on the other hand is like those success, I can demonstrate success by using like playing with another top player. But it's very hard to really theoretically to prove like under what kind of environment my algorithm is going to work and what kind of environment my algorithm is going to fail. So it's very hard to have very provable guarantees. In that regard, it's actually very hard, like this for me, so hard to convincing my industry collaborators to, hey, can you try some algorithms, even just for the smaller scale? Like, because it's very risky if we demonstrate those algorithms into the real people's life. So then what I'm going to emphasize this, right? Think about the challenges. So it's actually become even more challenge, like how can we really put in the RL for the network systems and still have some probable guarantees? And you can look at the bottom layer. So that's what I'm referring as the physical layer. And the top layer, I'm always going to use the top layer, means the decision-making or learning layers. So how I'm going to do it? So the message I'm going to tell you is this, right? So when we're dealing with those physical systems, the network system, transportation, power system, we have additional knowledges. And like, how about using the additional knowledges? So in the following of the talk, I'm not going to really fully explore all the knowledges. I'm just even ask one question. So I'm dealing with a network, and typically the network connectivity, that's the knowledge I have. Can I use in the network connectivity to boost my algorithm, to boost my learning? So how can I do it? So how are we going to really think about this problem? So I'm going to go through the problem setup. So in this problem setup, so like we are going to focus on the like the tabular MDP setting. So what this setting is means, so first of all, similar to any kind of MDP problem, we have the stage or the time, and each time t, so now we have individual agent here. So for here, individual nodes, they have their own state. And if you think about the transportation row, so that means how much traffic at each row section. So we have the state at each node. And for each node, it can take in some local control action. And for the transportation, again, you can think about this is how much traffic you can send into the next traffic, the row section. So for the action, so for both of the case, right now, we're going to assume in the final set. So that is standard tabular MDP setting. So what's the network I'm going to talk about here? So we're going to focus on one particular state transition rule. So in this state transition, now think I was mentioning, we have a local state SI, we have local action AI. So the state transition rule we're going to assuming is every node's next state will depending on his own state and his neighboring state and also his own action. So from here, like you can see this local interaction can define a network. So that's what I'm going to refer to as a physical connectivity. So in the learning algorithm I'm going to talk about later is I'm going to assume the particular PI value that we don't know, but the connectivity, that's an assumption we're going to assume. We know the connectivity. We know who are connected to who, and so how much connectivity individual person has. So now for each reward, so we're also assuming that everyone has their own individual reward. And also another critical phenomenon for here is we are assuming at each time, the local reward for each node or each agent is based on his own state and his own action. So the control policy, again, is a standard control policy. So we're going to assuming like it's just a mapping from the state to the action. And we're going to focus on the stochastic policy. So like taking from the observation to taking some random action according to the policy. So objective here, what I'm going to talk about is focus on the discounting reward, is I want to minimize or I want to maximize the expectation of the summation of the long discounting reward. So I want to also highlight, so we have extended the work to the limit averaging case with a little bit more assumptions, but for the sake of simplicity, we're just going to focus on the discounting reward in this case. So as I mentioned, I want to highlight, so one particular structure here is a local interaction. And we're going to assume in the local interaction connectivity, that's the system decision makers, as everyone will have. So there's some examples, like one example I mentioned is the traffic, and there's another very standard example that fit into this framework is the epidemic network. And for here, like the probability of individuals getting infected will based on his neighbors and whether his neighbors get infected. And another example, as I mentioned, the traffic network. And you can think about the congestion of a road will depend on the congestion of the nearby roads. So now let's dive into the problem, right? How are we going to solve this problem? So first, even we're not talking about learning, just think about the dynamic programming of MDP problem. So the one immediate challenge is the state and action space, because individual has individual state and action. And once we look at the global state, global action, it's quickly blown up. And so like this kind of problem, I think people know it for a long time because it's like in daily life, I've been seeing the network decision-making problem all the time. So I mentioned here, as a lot of analysis people have been spent on this problem, and we understand the complexity is exponentially blowing in the size of network N. And like the theoretical analysis, like more fundamentally intractability, like you can date back to even very earlier books and papers. And so recently, like there have been a lot of like progress in dealing with a multi-agent MDP. So like one simple thing we can do is we can just imagine individual learner, just like they just going to learn their individual decision making and ignore others' connection. So and it's like we can also do the linear function approximation to bring down the space, and like powerful function approximation, like we can use the deep learning way to do it. But I mentioned, right, it's really hard to prove, right? Do we guarantee any optimality? Like what exactly is the local, like the policies that really means compared with the original system? So that's the first challenge. And second challenge is this. So let's think about the policy. So I haven't talked about like what exactly the like constraint we're going to post on the decision-making policy. So I'm putting here like that's called information constraint. So this is like when I imagine I'm going to use in like if there is a powerful learner, a magic learner that can tell me what is a global optimal policy from the global state then to individuals' actions. And there's a one fundamental difficulty to implement it in reality is how can everyone get in the global state immediately? This is almost impossible if you think about really a large network that's spread out geographically. So what this means is motivated, naturally motivated the use of local policies. And what the local policy means is for individual decision maker making a decision based on the information that's available to you now. And here, this is an extreme case that we're going to focus on is called like fully decentralized policy. What does it mean is the policy we're going to develop is going to based on the local observation, like my own local state SI to my local action. So I also want to highlight here is as the algorithm, the framework I'm going to present can be easily extended to including more information to my local policy. But then one key factor is here is I'm going to make my decision based on the information I have access locally. So now let's summarize what the problem feature we have been talking about. So we have an individual state reward, and like we're going to focus on the local policy. But you can imagine, even my policy is local, but because my state transition rule are still coupled. So what that means is individuals' local decision, local policy is still going to affect everyone's long-term reward. So what that means is this: I still need some communication to learn what is the good local policy. So in summary, what the problem means, so it's here. We are going to using the local state. We are assuming we can observe the local state, local reward, and some local communication to learn a good local policies. And there's the local state, local reward, local communication. I highlight the color because what exactly local means, as in, I need a communication. So how much communication I need, so that's what we're going to talk about. So I hope the problem right now is clear for you. So now let's just think about how we're going to solve it. So we're not going to go fancy algorithm design, taking a standard IO algorithm to see, can we implement some standard algorithm in this problem? So I'm going to just focus on the active critique, the policy gradient framework. So for those kind of policy gradient framework, now in the full information centralized case. So the first step is to parameterize the policy. So here, the parameter I'm going to use is a theta here. So once I parameterize the policy, then I'm going to look at the projective function. It can be parameterized by the theta as well. So the policy gradient is just taking the gradient of the objective function. And the difficulty is how can you really get in the policy gradient evaluation? What is the delta J? So for here, this is the famous theorem, the policy gradient theorem. So what the theorem have been doing, and the thing I want to highlight here is this. So you don't need to remember the exact equation, but the thing I want to highlight is this. The policy gradient theorem, for this theorem, what is need the Q function. The Q function is expected long-term reward about my state action pair. So once I have the long-term reward estimation, so what I can do is I can use that kind of Q function to evaluate or to estimate my gradient. So the one critical thing is the Q function. This is the long-term reward. So, and if I have this kind of long-term reward Q function, and how can I really taking the gradient? It's kind of become very standard framework. On the actor part, I'm going to use the policy gradient theorem to using the policy gradient to update my parameter. And then for the Q function, because the Q function is the expected long-term reward. So what I can do is I can, based on my stage observation of the reward, to estimate the Q function, and we can do the TD learning or some other variation of the TD learning to do it. So, but as I mentioned, I want to highlight one thing here is the Q function. So the Q function, sometimes people call it as Q table. So the Q table is defined on the state and action pair. So the state, the full information centralized case means the global state and global action. As I mentioned before, the global state, global action, how many choices is exponentially growing with the 7 network. So this is huge table, and it's very hard to imagine who is going to restore this kind of Q table. And on the other hand, if I'm going to perform this kind of learning, the Q table, the S and A, they are global. But how can I really get in the global state, global action? So this is just a quick review of the centralized standard IO method. So now let's put into the network case, right? How I'm going to using that method to help in my problem. So for this one, as I mentioned, we're only going to focus on some local policy. And for this local policy, for individual agent I, so I have my local parameter theta I. So then the global policy parameter theta is just the augmentation of everyone's choice, decision choices. So I can just follow the definition. I put in my definition, hey, what is my Q function? My Q function is the expected long-term reward. And what is my state reward? My state reward is the summation of individual reward Ri. So I just do the simple algebra and change the order. So what I can have is my Q function can be defined as the summation of individual Q function, so Qi theta Sa. And you can look at here, it's we just change the order of the summation, and we can have something called individual Q function. But the thing I want to highlight here is this, because everyone's reward, the long-term reward, is still coupled by my local policies. So what this means is the local reward Qi theta here is still exponentially large table, right? Even I call it individual, but it's not really that individual. And what's the policy gradient? So for the policy gradient, again, I'm just like calculating what is a partial gradient. And the partial gradient turns out, again, it's needed using the global information, like I need individuals Q function to compute my partial gradient of the theta I. So this is the two challenges. And the two challenges I'm going to, like, in summary, put it down here. So just imagine a network. I'm putting a line as the example, as the way to visualize the showing. And I'm the one individual decision maker in the network. So how I'm going to do, how I'm going to like proceed, right? I don't have that much super powerful computation or communication skill to really having everyone's information. So how can I really do it? So that's the question. And you can take a 10 seconds to think what's your solution going to be. And I see there's a Q&A. Should I answer or let me see?
So yes, there's a question about what exactly does locality specifically mean here? You said the policy is local.
Yes. So I understand the first one, like the local, but I don't know the Markov blanket. You mean there's no Markov? So like, yeah. So I think Jenna, you can continue like probably pose a question if I don't answer your question well. So the locality here, what I was really referring to, like the first, my network system has a local interaction. Local interaction means that if you think about social network, so how much like you going to like your opinion will be changed toward one product, well, based on your opinion and like something if you try that product, and also your friend's opinion. So that means local. And okay, good. So I think he say like the question. So the reason I'm answering the question that time, because I want you guys to think about here, how are you going to make the decision making? So the local policy I was talking about is now I'm going to just making some decision based on my observation, but even for this kind of goal, I still need everyone's information to learn that kind of local policy. So I'm going to do it. So there's so many different ways, and I think in literature for the multi-agent system, like the mean field is a powerful tool. But the thing I'm going to talk about is different. So what are we going to do? Didn't work. Good. So the thing I'm going to talk about is we're just going to do the truncation, and I think it's actually quite intuitive. At least for me, when I make my decision, right, I'm going to think of myself. I will also look at my friend or like my family, like the people who is really far away from me. It's so hard to really worry about everyone. So here for this logic, I'm just doing the truncation. So then the one natural question is this kind of truncation really work? And what do you mean by the truncation? So here, the truncation, what I really mean is I'm going to every individual decision maker, I just going to have a small table S and A from a neighbor that's like, you can decide it how many neighbors, how many hops of neighbors you want to decide, but that's only like k hop neighbors. So I'm going to maintain some Q table in that way. And I'm kind of hoping just by looking at my neighbor's state action and then do those kind of TD learning, and then we'll have some nice structure. So then the question is this kind of truncated Q function really going to work? This is a very brutal step. And the nice thing is, for the network MDP, multi-agent MDP problem I was describing before, is actually has nice property for us to explore. What's the nice property I'm going to talk about? It turns out to have an exponential decaying property. So what the exponential decaying property really means? So this is a more rigorous like definition here. What it means is here, think about one agent I. So if there's another agent that's K who is far away from the person, from that agent. So then what's exactly the other agent is doing, like where the state and action that the K agent is at is not that important to my own Q function. If that agent changing from SK, AK to S prime K, A prime K, my Q function, like this is the global Q function, the change of that Q value is not going to be much. And how much the difference is going to decay according to the distance between myself and also that agent. So you look at this exponential decaying property, what does it mean? It means that if I just cut some person who is far away from me, it's not going to affect my Q evaluation much. And so then you wonder, right, what exactly will our system really have this property? So like this is a theorem, it's very general. We don't need much assumptions about the MDP. So we just like, if the reward is bounded, like, and plus some other standard assumption on MDP. So then the exponential decaying property holds. And the decaying factor rho, right? For the discounting case, I think everyone is easier to have the intuition because it is discounting reward. And once my action, my choices is affecting another agent, so it's already getting discounted multiple times. So that's for this one, you can see my decaying factor is naturally smaller than the discounting factor gamma. But I want to highlight, so even for the limit averaging case, so the exponential decaying property still holds. And in the discounting case, like the rho in the simulation, like we're generating many random MDP problem, and the rho will always strictly smaller than the gamma. And if you're interested about what kind of conditions need for the general network and for the non-discounting case, so yeah, welcome to read our last year, like the recent paper on the average MDP. So like this is actually very good news. It means even I do the brutal truncation, I still have a good approximation. And how good approximation I want to have, and I can control it. I can increase in my K, the K-hop neighborhood. So, and this is a good approximation. And what's the other one? So because as I mentioned, when I calculate the gradient, and I still need everyone's Q value to compute my full policy gradient, the partial gradient. This one is actually nice is because once I already truncated my Q function, so my Q function is not really going to depending on the people who is far away from me. And we go back to compute the full policy gradient. It's naturally to have this local summation property. So for the policy gradient, we can do similar things. We can do the truncation. And I just need to use my neighbor's Q function to evaluate my truncated, to evaluate my partial gradient. And because of the exponential decaying property, so we can show when if I'm going to use my HI theta, this is a truncated policy gradient, is going to be a very good approximation of the true policy gradient. And how small it is will depending on the decaying factor and depending on the distance, depending on how many K-hop neighbor we are going to look at. So now putting them together, you can imagine, right? The design the algorithm, it actually become like straightforward. Like we can just grab some centralized RL that you can have a more than one centralized RL and put in the multi-agent case and the things will work. So this is just like one simple example is thinking about the standard active critique policy gradient theorem, like policy gradient algorithm we have, we can just replace everything to the truncated version. And you can see the like line-to-line comparison. For the centralized case, I'm going to use the full policy gradient to estimate. And then for the scalable multi-agent case, I'm just going to use my truncated one. How am I going to estimate the Q function? So on the other hand, like just do the TD learning, really wait on the communication, the huge storage to getting all the information. But then if we like have all the information constraints, so then we can just use the truncated Q based on my neighboring information. So you have some local communication from your K-hop neighbor, and based on everyone's reward, state, and action, I'm going to update my truncated Q function estimate. And the estimation rule, the TD learning rule, can be very similar. Like putting all of them together, so we can have a rigorous guarantee of how good the policy is. So this is like one theorem from the paper. So talking about the sample complexity or the learning speed. So something I want to highlight is, let me see, can you see the mouse here? So like this one, the reason like for this paper, we didn't talk about anything like global optimality because I mean, in terms of global optimality, we actually have some recent funding to show some negative result, right? So there is, and we're connecting with some game theory literature. But for this one, because we parameterize the policy and the function itself, the MDP, once you're writing down the cost function, become highly non-convex. So this kind of standard guarantee to say the stationary or the gradient, so how the gradient has been changing. So, and like you can select the gradient, it will become smaller and smaller. And there are two components in the theorem here. The first component, so this is consistent with the centralized IO literature, like this, like the M means the iteration, like screw of M. So that's how much like the sample complex, the learning speed. And then for this one, so this is new. So this is because now I'm focusing on the local policy. And during my learning, I also did the truncation. So like the truncation, I say that it's negligible, but it still has some exponentially like decaying effect means it still have some effect. So this is a steady state error due to the truncation. And there's some like polynomial 1, polynomial 2, that will tells you how the learning will depending on the MDP structure. And there's one thing about the size of the network. So the one thing is in the complexity analysis is this, the algorithm for this one. So it's only going to depend on the largest state action space size of any k-op neighbor. So it's going to be independent of the size of the network. Right? Even like you have your N is growing like quickly, or you want to plug another person or like move another person. So the complexity is not going to change. So that's what we want. So we want the algorithm that can scale up to any size of network. And for the truncation error, again, like depending on the system property, right? If I really care about the accuracy, right, I can put in a bit more K, but this is going to be a trade-off between the storage, the communication, and also the efficiency. So that's the bottom line. And what like we actually did a different kind of numerical test to test the exponential decaying property and to show how good the learning algorithm is. So, and including some random generated MDP. So this is a network that we pick application, we pick from the wireless communication. So in this problem, so we have individual users and we have access points. So users trying to send a package, but if two users send the package at the same time, the package will be getting dropped. And arrival rate of each user, like the package arrival rate is random. So that's the setup that we have. And you can see is fitting into the local connectivity very well, because whether they can access to the same point, that means they are connected because their reward is going to affecting each other. So for this one, so what we compare, so this is one famous benchmark algorithm, Aloha, from the wireless communication. And for that algorithm, it's actually using some parameter from the stochastic MDP problem itself. And then for our algorithm, so you look at here, so we only tried a very simple thing. Like first is the k-op neighbor equals 0. What it means when I do my learning, I just kind of using my own information. I ignore everyone else. And even for this one, it will outperform the benchmark algorithm. And if we just add another, like just one hop neighbor, the performance dramatically increase. And so, but I still want to have the room of improvement. If this is a learning speed, right? Even though people will like score like 1 over score of m, like the good or bad. So for this problem, even we focus on the local policy, it's still taking like 10,000, 100,000 of iteration. And this still means there's a lot of room to improve. And that's what we have been working on recently is can we even bring even more physics into the learning algorithm to further speed up the method. So in summary, for the first part, so I have talking about the challenges to apply those real-time learning RL tools to the network societal system. And you see the challenges will raise up about like because of the application, like the storage, the communication, and many and the computation. So, and for our approach, what I was referring to is, hey, we can use in the network connectivity to do better, right? The thing we did is we based on the exponential decaying property and design a scalable IO method. So there's lots of ongoing and future work. As I mentioned, we finished the average reward case, and also, and I think like Guanan and like Adam, they carry out this work to adding more like information to the local policy to see how much improvement it can have. And like there are many other multi-agent IO setting, and for my own group, like we have been really focusing on like really interested into the optimization landscape of the multi-agent local policies, right? What exactly we can say about the convergence point, right? Which point is really leading to. And so there's some other settings, right? Because I'm always fascinating about the problem motivated by the real application. So there's another project I've been working on is on the thermal control for the large building. And for this one, like, first of all, hey, do I do in the MDP setting or do I do the continuous state, continuous action space setting? So like, it's a question. So then for this one, at least we have been trying another very different multi-agent network setting. So what this says is, right now, I'm not going to make any assumption on the network. This is a global system. I'm going to use in the dynamical system language to describing the state and action interactions. And the information setting is quite general. It's like, hey, every agent can observe some information from the state. And that's here, I call it as a XI, like it can be like different, like it can also overlap. Like the controller, if you can place controller there, then that's the controller. You can have the information, a local sensor send the information there. And then the cost, again, because it's actually hard to say the cost is only depending on my own state and my own action, right? The state will also, my reward or my cost function probably will be also depending on other state and other action. So again, we also put in a very general setting. It's just now everyone has their own cost, but the cost, who is going to affect the cost is a general function. So we focus on the linear system, so then we can have some analysis to be performed. I'm not going to give you the details, so I'm just going to highlight the difference compared with this work and the other work if you're interested in reading the papers. So for this one, as I mentioned, we didn't assuming the network assumption and the communication. So we still have some communication among different agents. So the communication we have, it can be different from the physical network. And that's in practice, that's usually what happens. You can build a very totally different communication to engage people's cooperation. So the algorithm for this one, we designed algorithm based on the zeroth order optimization algorithm. And the difficulty come to how can individuals devise to do the joint exploration and how individuals can do some global cost estimation. So we can guarantee high probability guarantee of the stability, and we have the sample complexity analysis. Again, is the result will be very the sample complexity in terms of big O argument, it will be similar to the centralized case, but then how the network or communication network going to change the speed is going to base on the spectrum of the graph. And as I mentioned, I'm not going to tell you how we designed the algorithm. This is some performance for this algorithm. And it's quite interesting for this problem, I want to say is from the simulation result, we actually don't need a huge number of iterations, and we can learn a good control policy. And what's the reason behind it? I will put in a question mark on it. So we the theoretical, the practice actually perform better than what our theoretical guarantees. So with that, I think that's my first part of the talk, and I just want to see the question. So the question from Borland is how to determine the value of K, how far away it is neighbor from the local state. That's a very good question. So as how good the K need to be will depend on the decaying factor. And how much how large and then what is the decaying factor? As I mentioned, it's actually complicated. For discounting case, right, the worst case is gamma. And then for the general averaging case with the true decaying factor, it will depending on the mixed in time of the MDP and some additional structure of the MDP. So right now, the math expression is complicated, and in practice what I've been thinking is I think before we really demonstrate those kind of online learning algorithms in practice, we probably need to do a lot of study and even run some simulation to figure out, hey, what kind of K value that we are happy with it, and then go ahead with that K. But so far it's actually hard to determine what exactly K, and again how far away is the neighbors from the local state similarly. So that's the similar question, right? Because in practice, think about transportation, right? Even if I say I can have a K equal 10, but then what exactly 10 means geographically, it's also depending on the distance and in terms of the communication, right? What communication structure is being available. So all those are exciting future work. So the next question, for the thermal control, could it be useful to include the readily available global parameter to the control or power consumption of the whole system? That's a good suggestion. So for this work, we okay, so there's some details. My answer probably go too technical. So for this work, actually, my answer is yes. So there's for that, let me go to the, for example, here, I call it the global cost estimation. So here we didn't assuming there's another way to get in the cost estimation. But if I have a more faster way to get in the cost, so actually I don't need using my algorithm from individual's observation to get in the global cost. I can directly using the information you point out to do a faster global cost estimation, and that is doable to put it into this algorithm. Great. Any other questions?
these are the only questions.
Okay, great. So given the limit of time, so I think for the next part of talk, I just want to give you the high-level idea. That's what we have been thinking, and I think it's very exciting to bridge in the online authorization, online learning, and the control society. So what do I mean by that? Like as I mentioned, this one we're talking about external uncertainty. So in the online learning from the computer science or authorization society, people focusing on lots of things on the worst case analysis. And here we take a slightly different perspective. So think of those applications I mentioned before, like the thermal control, cover control, transportation, like they always have some prediction available. And when we look at the data, like this is the real data from the ISO New England. So you can look at the actual load and load prediction, they're pretty accurate in short term. So, and transportation, I think everyone had experience, right? It's pretty good for the next probably 10 minutes. And there's a robotics application, right? For the like navigation, for the check-in, right? You can kind of predict what's going to happen in the environment in a short time period. So the question is like, so they have prediction available, and those prediction may not really in the worst case language. So how can we really use this prediction? And what's the fundamental value of the prediction? So what we did, like, I'm trying to explain the problem clearly. So the problem would happen, like, if I'm using a linear system to illustrate the idea, it can, like all the math I'm going to present can generate it to the nonlinear system. So I have a state, and the system, when you decide taking the control action, and then the system move to the next state, and then I will see a cost function. Or there is a cost function, that's what happened at the same time. So, and the system is just repeating in this process. So that the application, thermal control, robotics, power grid, many other examples. So now talking about prediction model. So the prediction model, to get in the story is simple. Let's look at a very simple prediction model that's kind of capturing what we did before. Is we're going to assume I have a look ahead window. And for the look ahead window, it's very accurate prediction. And beyond that, there's no prediction. So what the online like algorithm requirement is going to decide what the yield need to be made based on the local cost function and the cost history and some history state, the information we have. And as I mentioned, we're going to assume I know my system dynamics. So here assuming I know my A and B. I just think about for the prediction, how that prediction going to affect my algorithm. So this is the online algorithm information structure. And what's the like benchmark? So for the benchmark in this talk, like we're just going to really benchmark with a really powerful optimal control in hand side. So because this is a like dynamical decision-making problem, so the optimal controller, even with all the information available, there should be a time varying controller. And so that's what's our benchmark. So the optimal cost here, this is the like optimal cost if I know all the information. And this part is my online algorithm cost. So this like is slightly different from the static regret because here we allow the control action going to be changed. So it's actually very hard to from the, like if we read those online learning literature, it will say, hey, this definition sometimes is not really useful, right? Because you can always prove this is going to be like linear with time t, or going to blow up with the t. It's hard to have the sublinear t result. But our focus is different, right? Let's just use this regret as our benchmark and to see what analysis we can have. So like there's a lot of literature. So so those are literature from the, like this is actually from the standard control community. And this is recently there's a lot of papers from the like learning community also bring the dynamical system into the story. And like I said, if I focus on different kind of regret, I can have a very good regret analysis. But then for this type of like model predictive control, a very classical control tool, like what exactly the regret and what's the performance guarantee we can have is quite hard to have the analysis. And so that's I put the question like, hey, was a dynamic regret for this algorithm? And like additional, like, what is achievable? What is not? Like, how should I reuse my prediction? So like those questions, like those are for the general linear system, like dynamical system. So, but then if we look at a simpler problem, for the simpler problem, what I mean is the state, like just think about one dimension. And one dimension xt equal xt plus ut. And I can translate this problem to some converse optimization. And then a lot of like result can be available, like nice tools and like a good fundamental understanding of this problem. So when we study this problem, we ask the question, right? Can we use those online optimization tools or analysis to understand the online control algorithms? So this is let me zoom in. What exactly do I mean by that? So this is what I mean by simple case, just one dimension. Look at here, this is no AB. The system is very boring. But the nice thing for this one, what is happening is instead of my decision making control action is still EU. But for my decision making, when I try to compute, I'm going to ignore EU. I'm going to transfer the U to the xt minus 1 minus xt. So now this becomes a purely optimization problem. And I don't have a constraint. And why this is a nice structure? Because once I put in this one, I look at my objective function here. So here my objective function is a summation of local here. Now the local means the temporary local. And my current city will only based on my xt and next xt plus 1. So what this means is that if we look at the gradient descent algorithm, and this is the gradient descent of the global, again, the global means the long term, from t equal 1 to capital T. Look at the gradient descent algorithm, look at the partial gradient of individual xit. It has nice local coupling structure, right? So to compute the xt minus 1, plus 1, I only need this much information. This was the cost information I need, and this is whose state I need, say at t, say at t minus 1, t plus 2. So that's what I want to highlight. This has a finite temporal coupling gradient. So what does this mean is, let's assume, right, we only have a double look ahead window information. So what we can do? Can we really do those kind of gradient descent? This is how much information I have looking beyond, and my decision making is I need to decide xt plus 1. So suppose I can do any kind of initialization, I can do some initialization without using information. So that's using the online optimization literature. I just stay always assume there's no prediction. So I can use those algorithms to start. And once I start that, I can compute one step until here, because that's the information I have and that's the cost information I have. I repeat the process. Again, each time you will miss one information, you're missing one state. But continuing doing this way, what this means is I can using my limited online information to compute the offline gradient descent with W step exactly. And this gives us a very nice way to think, to analyze the algorithm or to think about how to use the prediction. So putting this one together, right? What is the online optimization control algorithm we can use is this, right? So each time I can receive the prediction, and then I initialize a new state. I backward compute all the state until getting the xt plus 1w, and then with the control action, you're just going to subject the xt. So because this setting, we can use any kind of gradient algorithm, other fast gradient algorithm can be implemented in this setting. And analysis actually become very simple. So what this says is taking any kind of online algorithm that's from the literature that people don't use in prediction, there are many of them. And once we have the prediction, so just perform the double step gradient descent, and then we can improve in the regret. So this is how much, if we assuming the problem is strongly convex, then the improvement is exponential improvement. And so that is how much, the value of the prediction. So, this is a very nice thing for the, simple case. So we have been really thinking about, how can the simple case story is nice. So for the general case, what's going on? And the key here is using the transit the problem to become unconstrained optimization. And then that's how the control can help. So from the control, we just want to really remove the U, but we still want to make the 1-1 mapping between the U and X. So then from the control society, what we can do is, so first we definitely going to assume it's a controllable system. For the controllable system, we can do the translation, convert the system to some canonical form. Once we have the canonical form, and what we can do, you can see this become very sparse, and there's only some value here. So what we can do, this is an example for the two-state system. For two-state system, for this system itself, I have one U and X1, X2. What really matters, I don't need the X1, X2 U at the same time. I'm going to remove the U by using the relation between the X1 and X2. And once I'm doing that, I put it into my objective function. Again, my problem becomes unconstrained. So it's unconstrained problem on the state, not on the action. And like the local, like if my C is convex, my problem is still convex, right? Look at all the things here. It's just a linear combination. They're still becoming convex problem. So because of this local coupling, as you can imagine, so my like partial gradient is still only depending on the locally state, locally in the time in the temporal sense. And we can still apply the original algorithm, but then for the two-stage system, you can see the local in is actually getting like a little bit exposed a little bit, right? Previously, I only need a t plus 1, but right now I need a t minus 1 and also t plus 2, t plus 3. So that's kind of implies the gradient step, what we can perform is actually getting reduced. So I'm not going to like tell you too much details of the algorithm, but like the thing I want to highlight is this: once we have a multiple dimension system, so then how much gradient step we can perform is getting limited. But then the analysis again from the online receding horizon, because we perform the real-time optimization control, so the offline gradient step, and again we can still improving the regret by examination factor. And this, how much it can be improved, now we're getting discounted by the size of network. And the size of network, it's not really the N, the dimension of the system, it's really more like what is the controllability index of the system. If you have more controller, you actually can make the system better. But so, and we put in this one to understand, right, what does that means for the real system? So this is for the LQR checking problem. If I just want to check a target, and the target is moving. So what's it got going on? And can we translate that kind of regret to this picture? So what it means is it has a two meaning. It's very nice view. So this one is means how fast my system is varying, the variation cost of path lines. If the system is really hard to check, it means the cost will be very high. But like if it's small, then it's actually easy. And the other one, how much the prediction is useful, is captured by the red terms. And more interesting thing is this one. We actually can have a fundamental lower bound, and the fundamental lower bound, like for the LQR checking problem, we can show like no matter how people are going to design the algorithm, right? Even go to more like complex algorithm as I showed before. Our algorithm is pretty simple, just a gradient based, but even just do any kind of fancy algorithms. So still the regret will be always larger than that bound. And like factor, you can compare them, they're almost the same. And interesting here is like how much the prediction is available. It will be getting discounted as my system getting more complex, and the complexity defined as a P, which is a controllability index of the system. So that's almost like the thing I want to highlight. And you can, as I mentioned, is we can generate the result to the nonlinear system. So we took this M3PI robot and non-harmonic robot do the checking. And from the checking, like the result, the intuition from the theoretical result is very consistent with the simulation result. If my prediction getting longer, you can see the checking getting much better. And when we look at here, when the check is not good, is when the checking point getting changed dramatically. And like my robot can not really have that ability to really respond to that fast. But if more prediction indeed helping my checking. So like this one should generate like putting a lot of like future work for us. And the following one can be very quick, just give you some ideas if you are also interested in this line of work. It's a prediction model. So the prediction model I had before is very simple, very brutal, like either you have prediction or no prediction. But in practice, we have some, like always have some limiting prediction, even for the very long term. And the prediction is getting inaccurate. So then like the recent work, we generate our work to capturing the inaccurate prediction model, right? At each time T, what my prediction about the tau is going like defined by the theta tau given at the T, and there's a true parameter at stage T. And so that's called like tau minus T step ahead prediction error. So what's in practice, what we will see is in practice, if you want to predict longer term, then the prediction error will increase. The like prediction accuracy will decrease. So, and the question, how to use inexact prediction. So what we want to have is like, so we want our algorithm will use the accurate prediction better, like more, but not going to use in too much of the inexact prediction, but then you don't know like what's like how inexact the prediction is. So then like we want the algorithm naturally to have that phenomenon. So like interesting for the algorithm I talked about before, we can just still applying the similar algorithm, pick a prediction window, and then just do the similar receding horizon like gradient opposite control algorithm we showed before, and we can prove the similar result. And now the result is going to have a 2 component, because one will also one is a similar thing like what I showed before, is a cost variation, how fast the external system is changing. And there's another part we're coming from, is this, the prediction error. And the case that prediction error, like if it's very inaccurate, then probably means I should use a smaller W. If it's inaccurate, probably I should just be more aggressive. And like for this kind of formula, what's the use of it? It can give us a natural trade-off, right? Depending on, like if you have confidence on your statistics, then you should just go ahead using a bigger W. Otherwise, then probably do more like conservative way of decision making and do more myopic way, not going to use a very long W. And so there's like, again, many other like directions, right? How can we really put in the constraint? And for the like more successful online control is model predictive control. Can we really understand why MPC, the model predictive control, is working very well in terms of the regret analysis and how much we can do? And like also put in the first part of talk and second part of talk together. If I don't know the system AB, can I in the real time do learning, but also in the real time to hedge the risk of in the future? How can I do it? So like in summary, as I put in like all this thing together, I think in general, like the ultimate goal is to do something like multi-agent, online, optimal control and learning, and to deal with like information exchange, dealing with the computation difficulty, and putting all of them together, like hoping we will have a very nice real decision-making rules for the real societal system. And thank you.
Thank you, Professor Li, for the great talk. So one question is about the your first part of the talk. So I was wondering, given a network structure, is there a way to determine whether it satisfies the exponential decay property?
Yes. So like for the discounted MDP, so it's always have. And for the like limited average MDP, so our paper have conditions, but the conditions is kind of conservative. Mm-hmm. So what we did is but we can compute some like random, like if I have everything, you actually can compute MDP. So the results, like the original intuition actually come from the stationary distribution. And the stationary distribution, you can see some decaying property. And those one, even our condition doesn't satisfy, but then you can still like do those simulation first, and then to check whether the decaying property holds. But the paper will have a set of conditions. Yeah.
Thank you. And as for the second part of your talk, I was wondering, what if your so here it seems you are assuming you know the system transition.
Yes.
So what if your system transition has some bias term which is unknown to you? So your belief of the system has some misspecification error.
Mm-hmm. That's actually a good question. So right now we didn't consider the setting. So we are working on like assuming the AB is unknown, but then we can do active exploration at the same time to understand A and B better. So and then for the case, what we can do is do the robust, for example, robust MPC. So like because I know my AB has certain kind of error, and especially if you want to have additional constraint like the state and action constraint, then you can put in the error into the consideration and taking the controller, making sure that you are not going to violate the constraint. So that's like called a robust MPC. But so for our own algorithm, we can specify, right, what kind of the bias you really want to mean, right? I can say the A plus delta and how the delta is, and ideally we want the learning can eventually making the delta getting smaller and smaller. Yeah.
So suppose there's some error which has, say, the operator norm bounded by delta, then will robust MPC have some theoretical guarantee?
Depends what kind of theoretical guarantee you mean. So robust MPC has many theoretical guarantees and come with many assumptions. But then in terms of like, for example, like if I really want to understand the competitive difference, I want to understand depending which benchmark you're going to put, it's very hard to know. But like robust MPC has a lot of like theoretical guarantee. It's just probably not really in the language that in terms of optimality, efficiency language, but in terms of stability or the constraint certification, there's actually like many nice results.
Thank you so much. And so that's all the questions I have. And thank you again for the great talk. And
thank you.
Thank you. And thank
you
you all
for the invitation.
Thank you. Thank you.
Yeah. Hi, Niao.
Hi. Yeah, great talk. Thank you so much for the talk. Yeah.
If you guys have questions, like also the audience, feel free to email me. I mean, I'm very excited about the general direction. There are a lot of things like we need to do together.
Thank you. Thank you.
Yeah, great. Thank you.
Thank you. Bye.
Bye.